Welcome everybody. Thank you for coming to this free webinar about HV electrical asset risk management. As we go through, if you've got any questions, please type your questions in the question box. They'll be monitored as we go. If we cover the material as part of the slide deck and the presentation, that's great. If we don't, then we can round back to your questions in 15 minutes of question time after the half-hour presentation. And if we don't get to some of your questions, then we can always, we'll record them and we'll get back to you by email after the session's concluded. So, the object of this session is to look into a range of issues around CBRM and CNAIM. And ultimately, there's a bit of confusion about what is CNAIM and what does it do, and what is CBRM and what does it do. So we'll try and clear some of that up, and we'll try and answer some of the questions like what's the CBRM methodology, how does CNAIM relate to the CBRM, and what are the differences, and how are they used in application. So first, the why. Why risk management? Well, here's a picture of the Deepwater Horizon oil pipeline pumping oil into the Gulf of Mexico that discharged about 4.9 million barrels of oil from September 14 onwards. And the disaster cost BP $65 billion in damages. So that's a pretty compelling consequence that you want to be aware of, and you potentially want to manage that risk. So what does risk look like in Australia? Well, back in 2019, I'm sure everyone remembers that we had some pretty severe bushfires here. And in response to that, there's been a lot of interest in quantifying bushfire risk, especially for overhead networks in Australia. For over 20 years, EA Technology has been working with our customers around the world to better understand probability of failure and end of asset life. And pretty early on, we realized that data could inform some of these calculations and some of these determinations. And so we came up with a condition-based risk management methodology to leverage your asset data to inform your assessment of the health of your asset portfolios, the likelihood of individual assets failing, pairing that with consequences of failure, and the likelihood by the consequence is the risk. Okay. So what are some of the use cases for CBRM and or CNAIM? Well, one of the main use cases is to reduce risk. So in that scenario, you might be experiencing too many failures. The cost of failures might be increasing, and you want to reduce the risk that you're running in your asset base. Well, you need to increase your capex to decrease your failures, but what you want to do is be able to prioritize the highest risk assets. So you need to be able to identify those high risk assets. And ultimately, in terms of a business case, you want to be able to offset the cost of the capex that you're spending by the reduction in risk. And we'll talk a little bit more about the trade-offs between reducing risk and how that fits into business cases in a little bit later in some other slides. You might want to maintain your current levels of risk. So you might be interested in controlling your capex spend and reducing it. And you want to maintain failures at acceptable levels, but also you want to be able to balance the risk against the benefit of deferral. So you don't want to be deferring work that's actually going to increase the risk, and vice versa, doing work that's not maintaining or stabilizing your risk. You might also want to use the modeling to predict the end of service life for individual assets. There are a range of ways of doing this. You can set a health index threshold at which you've defined it to be the end of asset life for that asset class, and then you can determine the years until it will reach that health index or that end of asset life. You might be wanting to do calculations where you find the net present value optimal year of replacement, trading off the deferral benefit and the risk reduction that you'll receive. And you might also want to compare the end of life that you're calculating with CBRM analysis to the end of your book life of your assets, the end of financial life. There's also tactical decision making, strategic planning decisions that you might want to make. So tactical decision making would be more day to day, week to week, month to month, where you want to leverage near real-time data to inform decisions about which specific assets would be most beneficial to treat immediately. You might want to also, so that's about asset prioritization. And you might also want to be able to find groups of assets that are geographically bundled to actually optimize the efficiency of the work that you're doing. So those are the sorts of tactical decision making efforts that you might want to use CBRM analysis for. Strategic planning, we're talking now sort of the 5, 10 and 15 years out. So you can project your health index profile and therefore your probabilities of failure and your risk out 5, 10, 15 years and work out what sort of program of works resourcing you're going to need, how you might want to smooth that profile. If you've got a big clump of assets that are coming up for replacement, you want to be able to make decisions about which assets you're going to bring forward and which assets you're going to move back, and you should be doing that probably based on the risk rather than other metrics like what their absolute health index or their age are. And in terms of the final the final use case here on this slide, reporting, we're all required to do a lot of reporting in our daily lives, from spreadsheets to planning reports to all the way up to regulators, stakeholders, the board, management. So this is something where CBRM and CNAIM can be a great translation layer between engineering and management and other consumers of your reporting information. So it makes it much easier if you've got a system which can deliver you a bunch of results and graphs that you can then feed into your reporting, and that goes for regulatory funding, AER submissions, and internal and external reporting to stakeholders and the community. So that brings us to the first key calculated output of CBRM and CNAIM. And you can see in this top right-hand corner of the slide, there's this sort of Venn diagram, if you like, stylized Venn diagram. Now, CNAIM is a subset of CBRM, and we'll go into a bit more discussion about that. But just to allude to that, CBRM is the overarching methodology, and CNAIM is sort of a restricted application of CBRM. Okay, so in the CBRM world, you've got an analog health index that runs from a minimum health index of 0.5, and due to the exponential nature of the function and the aging curve, you can't have a health index of 0. It would break the formulae. So you start with an as-new health index of 0.5, and as the asset ages and deteriorates, it can progress in the current year as high as a health index of 10. Okay, you can see some descriptive terms about what that looks like. When they're in the green zone, 0 to 4, they're in a good or serviceable condition, or close to new or as new. As they get into that end of expected life period, there's evidence of the onset of degradation, and as they get further out into the end of asset life area of a health index of 7 and above, you can see measurable degradation, and you should be considering refurbishment or replacement of the asset. Now in CNAIM, you'll calculate an analog health index and then you'll allocate it to one of these buckets. So there are 5 buckets. And the output of CNAIM is a risk matrix. The output of CBRM is a discrete monetized risk value for each asset. Okay. So the health index has got a well-defined mathematical relationship to the probability of failure via certain constants, K values, C values, and the HI limit. But where does this relationship between asset health index and probability of failure come from? Well, it's derived from the Weibull failure curve. Okay, so here's an example of a Weibull failure curve. And on the right, you can see that we've split out the, so the Weibull failure curve relates time on the x-axis to the probability of failure or the failure rate on the y-axis. Now, you'll also notice that we're not interested really in asset management. We're interested in end of life rather than in the early life of the asset. So for mathematical simplicity, we simplify the curve and we make the 0 to 4 health index to POF relationship linear and flat. Okay, so we're ignoring those early life failures, which are largely manufacturing and installation defects. Okay, and we relate age to asset health index and then asset health index to the probability of failure. Okay, now in terms of the mathematics of how that works, you can look up in the common the CNAIM, the Common Network Asset Indices Methodology documentation, the exact formula that relates health index to probability of failure. It's a Taylor series approximation of an exponential curve. But in CNAIM, they have commonly agreed K values for each of the asset classes that are modeled. Whereas in CBRM, we define a number of failure modes, and then we do this exercise of curve fitting. So the K value that we use in CBRM is tailored to the known or expected failure rate for that failure mode for your assets in your operating environment and your network. So that gives us a lot of flexibility. If we're working with industrial customers, we can actually look at using K values that we've used for other networks in Australia, or for you know, or using the K values that they use in the UK. Whereas if we're working with DNOs in Australia, we can calculate the K value that's currently being experienced, and then, you know, again, do some benchmarking, compare that to what's being seen around the world. So risk. So as we said before, risk is the likelihood of the event multiplied by the consequence of the event. So we calculate our asset health index and probability of failure for each individual asset. We calculate average consequences of failure. So for example, for the network performance risk category, that would be things like the value of the lost load or the cost of an outage. All right, so if you're an industrial customer and, you know, a stoppage is you know, if you have an electrical failure, you're going to experience a 24-hour production loss. Those would be average consequences. And then we leverage the data available to work out individual consequence modifiers for each individual asset being modeled, so that we can tailor the risk exactly to the risk of that specific asset in its operating context. Now, again, there's a distinction here between CBRM and CNAIM. So in CNAIM, it's prescriptive. The consequences and the consequence modifiers that you can consider for those assets defined within the methodology, and then you work out what they are in terms of percentage of the average consequence across the asset class, and then they get assigned into criticality buckets, C1, C2, C3, and C4. So the object in CNAIM is to get a picture of your risk matrix and see, what the numbers are in each of these individual boxes. And the higher the numbers are in the bottom right of your matrix, in that red quadrant, that red corner of the matrix, the higher the risk that you're running in the network. And then the object is over time to try and move the assets from the bottom right quadrant towards the left and the top of the matrix by spending capital. Or if you're running an acceptable risk profile, then it's to maintain it and not to see assets slip into that bottom right corner as you control your CapEx spend. So, risk predictions and cash flows. Now, this is really CBRM specific stuff, and this is the power of calculating individual monetized risk for each asset in your asset class and your portfolio. You can determine the current risk that you're running per year. You can determine your future risk. So you calculate the individual risk for each asset, sum that up, and that's your risk in the current or a future year. But what we're really interested in is the delta risk. Now, this is the difference between the future risk and the risk associated with a new asset. So this is effectively the risk dividend that you can get by either refurbishing or replacing the asset. So this is the value that you can unlock by doing work and spending capital. So this is the cost that you can offset against the cost of the work. And a risk cash flow is the delta risk in a particular year. So obviously each year there's a risk that you're carrying in your network and a delta risk. And if you do nothing, that delta risk is going to increase year on year. And the net present value of all of those delta risk cash flows summed up is the total risk cost over the planning window. Okay, and so you can calculate your risk cash flows in option A or scenario A, you calculate your risk cash flows in option B, and so on and so forth, and then you can do an options analysis, and you can also include the risk cash flows for the cost of doing something and in what year. Now, I want to hone in on this point because it's something that's sometimes overlooked. The risk is an actual cost to the business, whether you recognize it or not. So in the case that we saw initially, there was a $65 billion cost to BP that they had to pay, right? So if you worked out what the likelihood of that happening was based on the condition of the valve that was put in on that particular installation and what the probability of it failing was, and then multiplied that by the 65 billion, you could have worked out what those risk cash flows were year on year, and then you could have offset that against the approximately 200,000 or something it would have cost to buy the new part. And I don't know how much it would have cost to fit that new part. But those are the sorts of, they are actual costs to the business, and those risks are out there. You know, sometimes you're lucky, sometimes you're not. We've had 2 1 in 100 year floods in 40 years in Brisbane. So those costs are real, and you'll pay for them eventually if you're not managing your risk effectively. So this is a case study of CBRM in action. So recently we helped one of our customers with their AER submission for poles. And in the right, you can see a graph which has got the net present value of cumulative delta risk under various scenarios. Okay, so there are 2 base cases which act as bounding functions in the graph. The base case 1, which is do nothing, is obviously not an option. You have an obligation as a network provider to not have poles falling over and potentially injuring people all over the place. We've got a high burden of safety in the electrical industry, and that comes out in the modelling. Safety is usually quite a small part of the risk stack because we do operate very safe electrical networks in the power industry. Base case 2 is replace all assets in a future year. In next year, right? So this is if you could wave your magic wand and all your networks were replaced, or all your assets, were replaced overnight. What would that look like in terms of the risk profile that you were running? So you can never eliminate fully risk, right? But we know intuitively that spending billions of dollars replacing all of the poles in one go would be gold plating the network and would not be economically viable. So this is really modeling the non-economically viable option of gold plating and replacing everything in the network. And then within those two, there are a range of sort of viable options where you can decrease your capex and increase your risk, or you can look at what the effects of certain proposed programs of work are. Okay, so in this particular case, the AEARN made an initial offer based on their RepEx model of $100 million for pole replacements over 5 years. The DNO initially requested in their preliminary submission $250 million over 5 years. In their final submission, they ended up requesting $200 million worth of funding, and in their final determination, they secured $148 million of funding over the 5 years. So, and in the response, the AER said they were satisfied with the risk methodology that was used, but they questioned some of the results of their pole assessment algorithms. So some of the inputs that were feeding into the condition end, or the health index end of the modelling. So they had a separate model that they were using to assess the residual strength in the poles, and that was what the AER broadly was questioning, because it was a new methodology and a new model that they were using. Okay, but this shows that when you make arguments based on a bona fide risk methodology that's accepted by the AER is willing to accept those arguments, and they were able to secure a 50% increase or a 48% increase over the 100 million that the AER was originally planning to offer. So, and in here you can see a range of scenarios. So the top two, the riskiest ones, were compliance poles and what the AER was modelling with their RepEx model, which was just basically replacing unserviceable poles. So that's arranging the poles based only on health index. Okay, and then our modelling showed that if you just increase slightly the amount of poles that you're doing, and you get to smooth your resourcing profile, bring forward the high risk poles to do first, and have some discretionary poles, so you're not just in the tyranny of replacing unserviceable poles, you're actually replacing some poles based on their risk and bringing those ones forward. And then if you have to defer any, you're deferring those ones based on their lower risk. You could actually get this huge reduction in risk, which is unlocking value for customers, shareholders, and the economy at large. All right, and the second case study I've got for you is a case study for industrial customers, an industrial customer rather. So we did a big job recently where we went and assessed cables at a facility. It's quite a large facility that handles coal. And so obviously any outage for them is completely unacceptable. This facility runs 24 hours a day, 7 days a week, 365 days a year, and they get a shutdown once every 7 years or something, right? So reliability is absolutely key, and they can lose a lot of money for any shutdown in the facility. And that's a sort of a common thread with, I mean, even industrial scale beverage production. You know, you have an outage and, you know, it takes 8, 10, 24 hours to get the facility back up before it's, you know, putting product out the other side. So we modeled and you can see that this NP means network performance. So you could read that as reliability or, you know, cost of an outage, right? So the dominant risk in this case study is the reliability, network performance, because it's so expensive to have an outage of that coal terminal. And then, you know, here there's a safety risk on top there as well. Okay. Now, just by doing a couple of small jobs, I think we worked out it was sort of about $50,000 or $50,000, $60,000, $70,000 worth of work. You could reduce the 10-year risk from $485,000 to $19,000. Okay, so that's you know, it's sort of roughly 5 to 10%. Sorry, to like 10 to 15% of the risk that you're saving to do the job, to reduce that risk from $485,000 in today's terms to $19,000 in 2021 dollars. So that shows you the power of this of CBRM modeling when you want to really start putting together business cases and working out what the cost benefit of doing work and not doing work is. All right, so that brings us to the end of the presentation. And so in conclusion, I'd just like to highlight some of the differences between CBRM and CNAIM. So CBRM stands for Condition-Based Risk Management, and it does what it says. The Common Network Asset Indices methodology is a benchmarking and reporting tool that's in use by the DNOs in Great Britain. So what's the relationship? Well, CBRM is the initial methodology that was developed, and it's the overarching methodology. And so CNAIM is simply a restricted implementation of CBRM. The data, all right, so for CBRM, we use available relevant data, and we would also suggest to customers, based on our experience, these are the data that you want to be collecting to best leverage information about the condition of your assets, the likelihood of failure, and the risk associated with those assets. The common methodology has got fixed data fields. It's all fixed and it's all defined within that methodology and that document. And you're not allowed to include other data points. Otherwise, you're not following the methodology of CNAIM. What's the recommended usage for both? Well, CNAIM is a benchmarking and preliminary health and risk assessment tool that's used by all the DNOs in Great Britain. It's getting popular around the world. People are asking about it and implementing it in Australia and New Zealand, because we often look to the UK for proven in use technologies that we can deploy in our own networks, in our own setting. But it's great if you do want to compare yourself to other utilities, and specifically utilities operating in the UK. But CBRM is bespoke asset health and risk modeling that, you know, you tune over years, and you get better and better, more accurate health index and more accurate risk results. The more familiar you become with the methodology, the better you've got it calibrated, and as you improve the richness and resolution of your data, you'll improve the richness and the resolution of your outputs, your health and risk outputs. So what sort of questions do they answer? Well, CNAIM can tell you how we compare to other utilities using the methodology. What should our asset replacement budgets be over the next 8 years? That's really what it's used for in the UK. Ofgem mandates all the DNOs to report and do the regulatory submissions using CNAIM. And the 2.0 methodologies, if it's not out, it's coming out shortly. And are we reducing our network risk year on year as we deliver our replacement program of works? And what can CBRM tell you? It can tell you how much you can reduce your future expenditure without impacting your performance. Which assets do you urgently need to get off the system? Is the asset plan delivering real benefits, real financial benefits to your customers, your stakeholders, and where are the significant safety risks on your network? That's another one that people often want to understand from CBRM, and in Australia that often means that you need to start modelling bushfire risk, and CNAIM doesn't have bushfire risk as part of the methodology because it's not a problem that they face in Great Britain. All right, so that brings me to the end of my presentation. So I guess now we can move on to taking questions. So has anyone got any questions? I'll go to Jack. What are the key things to reduce delta risk? Right. Well, I guess the first thing you want to do is understand where the delta risk is and be able to accurately model that over a 5 or 10 year time horizon. And then you can sort the outputs of the model based on high to low delta risk. And then you can start looking at those assets and you can start working out which ones in which year there's a cost benefit for replacing or refurbishing those. And then you can model that in the CBRM interventions module. So it depends what you're doing, whether you're spending dollars to refurbish, like in the case of poles to reinforce the pole, or whether you're actually going to replace the pole. So pole reinforcement usually gives you another sort of 10 to 15 years out of the pole. And a replacement obviously gets you a brand new pole where you're thinking you're probably going to get 50 to 70 years out of the pole. So, but that would be the way that you would use the modelling to rapidly reduce the risk in your network, is to produce those individual delta risks for every asset, and then sort high to low, and start having a look at how you want to organise a program to tackle those assets. Oh, okay. So specifically in the coal facility example. Oh, okay. So that was there were a couple of areas where the cable had been damaged. Okay, so it had been nicked. Someone had, there's a lot of machinery moving through the site. Someone's bumped into it and abraded the sheath, and it's right next to the ocean. So obviously the environment's quite corrosive. So that got into the metallic sheath of the cable, and it was starting to puff up, and so the mitigation was, if you cut out that section of cable and rejointed it, okay, and reduced the condition factor by removing that problematic section of cable, what does that do to the health index and therefore the POF, and over what time horizon? So when we modeled that in CBRM, you do that job and it costs you $20,000, say, then, and there was a couple of things that needed to be fixed. That's why I added up to about 50, 60,000. And you do these couple of small jobs, and that reduces those condition factors on these cables, which then means that you could see in that graph, if we go back to it, you see it really scales down the delta risk in the current year to 0, and it's not until you get to 2026 that you start to get the health indices then popping up into that point where you're actually going to get some delta risk. So that's how the risk modeling was done for that customer to understand what the cost benefit of doing those cable remediations was. Right, so the question is, how would you use this model for a known issue with workmanship based on a number of failures to the wider fleet, e.g. Cable terminations on switchgear cores and switchgear above? All right, that's a great question. All right, so in both CBRM and CNAIM, there's a factor that's called the generic reliability factor, okay? So that's exactly for this scenario. And in the UK and in Great Britain and with the common methodology, there's some very specific wording around how you should apply the generic reliability factor. And one of the things they mention is NETRS. Now, NETRS is a database of asset failures, electrical asset, HV electrical asset failures that that we set up for the UK power industry. So all the UK DNOs are subscribed to NETRS, and when they get asset failures, they put that in the database. So that then, you might have a small population of those assets in your network, whereas there's a lot more of those assets in a broader context that you can leverage off their experience of how they're failing and whether there are reliability and type issues with those assets. But your question's more really about, so there's an installation issue. So this might be something like in the electrical industry, I've seen it where there's a type issue with switchgear and there's, some sort of discharge going on between, the way they've got the barrier boards configured, or another one is, crimping dies that they use in conductors. And, if there's a fault with a crimping die, it doesn't crimp correctly, and then over time those conductors start to pull free and you get lines down. Those sorts of manufacturing or installation issues. Well, if you can identify the assets that are susceptible based on the manufacturer and type, or some kind of combination of the manufacturer and type and the year of install, then if you can classify them as generically unreliable, then you can apply a generic reliability factor to them, which will push their health index up, which pushes their probability of failure up, which then is evidenced in the risk and the delta risk at the end. And so then you go through the same process of you set the generic reliability factor that filters out in the modeling, and then you can sort high to low delta risk, and you can identify those ones, and they should float to the top. But again, this is about considering everything on an even playing field, right? So there might be higher risk assets than those, right? And they'll still be higher risk, but at least you've pushed those assets with that type defect, that installation defect, into that top cohort. But that's the good thing about CBRM. If once you've applied the methodology correctly and you've got rich data informing the modeling and the calibration is tuned correctly and you're getting accurate health index, POF and risk figures out the other end, then you're treating every asset in the same way. And so you're not favoring one over another. So in bigger organizations where there are different asset managers with their own barrows to push, you're putting all of the data in, everything's getting treated the same way, and then the results that you get out the end are believable, and they're the results, and you should follow them. So it takes away some of that friction about about making decisions about one asset over another. What's the next question? I would call it the cowboy factor. What's that? That's a good comment. I think we'll take that as a comment. I would call it the cowboy factor rather than the generic reliability factor. So cowboys have installed things incorrectly and they're failing. Very good. What was the basis for establishing residual strength value of the poles based on the current industry standard of drilling into an otherwise sound pole. Sound dig and drill. I don't think they drill every pole. No. Drilling poles for sound wood is sort of an end of life invasive test that you do. Obviously you're going to test the pole to see if it's hollow before you drill it, and the more you drill a pole, the weaker you make it. So I'm not really here to comment specifically on the nuances of how that utility does their pole inspection, but what I can say is that the AER is not really an engineering organisation, right? And even within organisations that we work in as engineers, there are a lot of non-technical people who don't understand technical things. They understand money and cash flows and things like that. So what I would say is that CBRM really is a translation tool that can decode engineering into a format that economists like the economists at the AER can understand, which is monetized risk cash flows. Okay, and the language that the AER uses is things like, we weren't convinced, and we spoke to our consultants and they questioned some of the calculations and the measurements, or some of the parts of the methodology, so therefore we weren't convinced as economists that the model was working effectively. I think really what it comes down to is you want to be mature in your approach by the time you're putting together a submission to the AER, right? Because if you're mature in your approach, then you've got all the documentation behind you, you've ironed out any problems. So it's a bit like, you try to show someone something and it won't work for me right now. That's what happens when you try and deploy a new methodology or a new system of modeling while you're going through a regulatory process. When things go wrong, the AER just says, oh, look, you haven't given me confidence that your modeling works properly. So, and you need, there's a lot of tuning that needs to be done. And this is where some people, in my experience, have come unstuck in presenting to the AER. They've actually produced good models and they're not tuned properly. And then the results that are coming out the other end look like an ambit claim, and they look way out of whack, and they don't pass the sniff test. And therefore the AER says, well, these can't be right. So then your model can't be right. Well, the model might be right, but it just might not be, the calibrations might not be tuned correctly. So in that case, the AER will say, well, we don't have confidence in the results of your modeling. And then that sort of defeats the purpose of having done the modeling. So it's really important to have people that understand the assets and also understand what the results should look like, and so they can perform that sniff test and say, hey, look, something's obviously wrong here with the way we've got it calibrated, because the results are just not believable. Right, I think we've come to the end of the question time. I'm happy to keep going for another few minutes with question time, and are we going to get cut off?
We'll receive the questions, so we can email them personally.
All right, so do we have time for one more question, or is it? All right, yeah, okay. So the next question is, how is the health assessment data fields being normalized for comparison in CNAIM? For example, some countries using mostly overhead lines for power transmission, whereas some are underground cables. Acid age replacement may be a different factor from countries. Thanks. Okay, so right. So how are they normalized? Well, the way that the calibrations are put together in the common methodology is that representatives from each of the DNOs that's using the common methodology, plus representatives from EA Technology, form a working group and then work through it and come up with calibrations that suit the UK and the working group and the DNOs, run the figures through and then sense test it and go through that calibration process I was alluding to before. And then they fix those values and everyone agrees to use those values as part of the common methodology. Now, in terms of, I guess there are a lot of networks in the UK that are predominantly underground, and there are some networks in the UK that have got a large amount of overhead. I would say that in Australia, we've got far more overhead than they've got in the UK. And so we've probably got better experience with, overhead assets and overhead networks than they do in the UK. But I don't think they go through an exercise of benchmarking underground versus overhead assets. They treat each asset class individually. And so overhead assets, conductors, poles, cross-arms, are treated very differently and separately as separate asset classes to underground assets like cables, joints, ring main units, and so on and so forth. So hopefully that answers your question. How should you account for the effects of unplanned in-service asset failures in risk forecasts? Unplanned in-service risk forecasts. Well, the CBRM methodology will match. So the sum of all the probabilities of failure for that failure mode will add up to the known failure rate, because we actually now give you the option in CBRM of toggling. So you can fix a K value, so you can see what it would be like if you use the K value that they use in the UK, or you can then calibrate the K value to match your specific assets. But in essence, the sum of the probabilities of failure add up to the known failure rate. So then that's how you can perform a calibration. You can check that when you're multiplying all those POFs by the consequences for the individual failure, that the figures that you're getting out the other end are within the ballpark of what your stiffest penalties, or how you're tracking with your stiffest targets, and what the cost of those S factor values are, or if you're using VCR calculations. So there's a subtle nuance here, right? So we'll produce models that will allow you to calculate your network performance value of lost load two different ways, and you can toggle between the two different ways. So one way is to look at it in terms of the S factor. Now the S factor is the stiffest penalty reward, and that's really important to the internal stakeholders and the shareholders and the board and management, because that's a cost to the bottom line of the business, or a benefit. Whereas when you're preparing a business case to the AER and externally reporting and reporting to customers and external stakeholders, you really want to be looking at the VCR, and the value of customer reliability is the dollars per megawatt hour, right? And those figures are all published by the AER. What are acceptable VCR values? You just have to go looking in their documentation as to what those VCR values are. And there's like an overall network VCR value, an all-encompassing one, and then there are VCR values based on the geographic region, rainfall for residential customers. There's an agricultural value, an industrial value, a commercial value, and so on and so forth. There are these different VCR values. Often it's very difficult to properly account for what portions of the feeder loads are agricultural or industrial or residential. So that gets a bit tricky, and sometimes it's easier just to use the overarching VCR value for the whole network. But really, you want to make sure that whatever your output of your modelling is, that it bears scrutiny, and it's not like 5, 10, 20 times what you're actually experiencing in terms of your S factor you know, penalties or undershoot of your targets per year, right? Or overshoot of the baseline, if you know what I mean. So you want to make sure that those reliability figures are accurate and you're calculating an accurate network performance risk. But I mean, the original question was, what was that question? Yeah. So that's how you would account for the effects of unplanned in-service asset failures in your risk forecast. You quantify, you know, how many unplanned outages you think you're getting per year. You calibrate your failure rates to that. You calculate the network performance cost of that, safety if there is any, the OPEX costs responding to those unplanned outages, and any environmental costs, and then you define that as a specific failure mode, right? So usually we'll split it up into 3 failure modes. So the first failure mode will be that there is no planned outage, but you have to do you have to schedule additional maintenance work for the asset because there's some sort of a failure that needs rectification. So it's unscheduled maintenance. And then the second failure mode would usually be sort of like a significant failure where you do get an unplanned outage, but you don't get, it's not a catastrophic failure. The plant doesn't explode, it's just an unplanned outage. And then the third failure mode would be the serious or catastrophic failure where you get an explosive failure and there's additional damage and it's a longer job to repair and reinstate the asset, and so that's got higher costs associated with it. So hopefully that answers the question. Does this case study can be mitigated more through the proper selection of equipment and regular inspection and maintenance? All right, so look, you can choose to manage risk through increasing your inspections. Now, how you model that? Obviously, there's an additional cost for the increased inspections and maintenance, and that has to get put into the cost benefit analysis as a recurring cost. But what you're doing when you're inspecting the assets more regularly is you're shifting the failure mode. Okay, so I just mentioned the 3 failure modes we generally model. So failure mode 1's minor, failure mode 2 is serious, and failure mode 3 is major. Okay, so major, boom, you let the smoke out, there's an explosion, secondary damage, big cleanup, longer repair. Failure mode 2, unplanned outage, right? So the protection operates correctly, and you know, and somehow the asset doesn't explode, and so, but you do have to perform a repair. And then failure mode 1 is you just doing inspections and minor repair works. So what you're doing in your scenario that you're proposing is you're doing additional OPEX expenditure year on year for 5 or 10 years, and you're hoping to catch that asset before it fails as a failure mode 2 or 3. Okay, so you're trying to shift some of those 2 or 3 failures into an F mode 1, where you can actually do something about it before you get the outage. So it's possible, and that's how you do the analysis. You work out how much am I reducing the risk by shifting that failure from a failure mode 2 or 3 to a failure mode 1, and how much does that cost? And to be honest, the best way of doing that now is through monitoring. Okay, so there are lots of different styles of monitoring. We offer partial discharge monitoring for cables, permanent installation, and for switchgear. And what that monitoring solution will do is it will constantly record those PD signatures. It pushes that data up to the cloud, and then we've got algorithms that run over the data and highlight anything that's of interest. And then we've got key trained staff that review on a daily basis anything of interest and have a look at the results of those monitors, and then can alert customers when something's kicked off and there's a potential for a failure. So you get advance warning before one of these failures. And that's usually more cost effective than sending people to walk the kilometers of cable run every day or every week to check it. So, all right, hopefully that answers that question. I think we're all done with questions. All right, thanks everyone for attending. I hope you all got something out of it. We're planning on running some more sessions like this, short half-hour sessions to highlight topics of interest in the risk management space. And so hopefully I'll catch you guys again in future. And any of the questions that I didn't get to now, or if you've got any follow-up questions or you don't think I answered those questions fully, please just feel free to email me or my team, and we will get back to you. Thanks everybody. Have a great day. Stay safe.